Hey everyone, welcome back to Real Analysis 1. This will be lecture 2 of the course. And in this section, we're going to discuss a number of things, a couple of things. Probably the most important thing that we'll look at is a property of the real numbers called the least upper bound property. So let's go ahead and jump into it. We're going to call this section 1.2, the least upper bound property. Okay, and before we delve headlong into the least upper bound property, we need to review some of the algebraic properties of the rational numbers and the real numbers. So let's start with a review of some of the algebraic properties of the rational numbers and the real numbers. Okay, now this will be very obvious and clear if you've taken an abstract algebra course and you're familiar with the concept of a field. But even if not, I think going through this will be helpful in that it'll give you a better understanding, I think, of some of the complexities of these two number sets. So as I just said, Q and R are algebraic fields. Now, what does a field mean? In short, what a field is what it means for Q and R to be fields is that they are endowed with two operations and they satisfy a list of axioms. So in short, I would say, this means that they have two operations, right? And so the operations are nothing cryptic there. It's addition and multiplication. And they satisfy the following axioms. Of fields, right? So what are those axioms? Well, let's go through them. Many of these will be familiar to you. Some may not, right? Depending on your background. Okay, so the first thing is that, so these are the field axioms, right? So if A and B are in a field F, then A plus B is in F and A times B is in F. Okay, all that. So this is a concept known as closure, right? So if you've taken abstract algebra, you know exactly what I'm talking about. But if not, what that basically means is that if you're inside the field and you do these operations on two elements inside the field, then you don't ever get outside of the field, right? So this is the concept of closure. Okay, and the rational numbers and the real numbers are indeed closed. If you're in the rational numbers and you add two rational, meaning if you add two rational numbers, you're going to get what the result will be is a rational number, right? If you multiply two rational numbers, you get a rational number, right? And obviously the same is true for real numbers. Second, in all of these cases, A and B are taken from the field, right? So A plus B equals B plus A in a field, and AB equals BA in a field, right? So in a field, all elements commute, both operations. Okay. Thirdly, A plus B plus C equals A plus B plus C, right? So this is associativity, right? I can do the B plus C first and then add A, or I could do the A plus B first and then add the C, right? And the same is true for multiplication, right? So this is the associativity property. Okay, so those are things, I mean, these number 2 and 3 are things you've certainly seen. One is maybe a new idea, but I think it's fairly straightforward, especially when you're dealing with rational numbers and real numbers. I don't think wouldn't require a lot of convincing on my part to get you to believe that two rational numbers added together make another rational number, for example. Okay, now beyond this, some of these may be a little bit strange to you if you haven't been through abstract algebra and you're not familiar with some of these ideas. But the first one that we want to talk about, number 4 here, is that there exists a 0 element in the field such that a plus 0 equals a for all a in the field. Okay, and so this is what's called the additive identity. This simply means that this 0 element has this special property that no other element in the field has, right? Meaning you can add it to anything and it changes nothing. Okay. Fifthly, there is this idea of there being, so for all a in the field, right? So for every element in the field, there exists a negative a in the field, okay, such that a plus negative a equals the additive identity, right? And so what are these negative a's? These are called the additive inverses. Okay, so meaning for every element there's one and only one element which when I add to that element gets me to the additive identity. Those are called the additive inverse elements. And in a field, every element has an additive inverse. All right. Number 6. Similar to number 4, there exists an element usually denoted as 1, certainly in Q and R denoted as 1. There exists a 1 in the field such that a times 1 equals a for all a in the field. Okay, now this is going to be the analogous concept to the additive identity, but for the multiplication operation. So this would be the multiplicative identity. This is the multiplicative identity. Right, and so there's no other element besides this element 1 that has this property, that when I multiply it by anything in the field, it doesn't change the element. That property is reserved for just the multiplicative identity, and there's only one of them. Okay. Number 7, similar to number 5, for all a in F, for all elements in the field, and here we're specifying a not equal to 0. For all non-zero elements in the field, there exists a inverse in the field, a to the negative 1. This is just notation. There exists this a to the negative 1 power such that a times a to the negative 1 equals 1. Now this is just notation. Don't get too hung up on this idea. But this is really analogous to the additive inverse. So this is analogous to the additive inverse idea. These are the multiplicative inverses. Right, so for example, the number 10 in the rational numbers, 10 over 1, would have a multiplicative inverse of 1 over 10. Right, I multiply those two together, I get 1. And those are called the multiplicative inverses. Okay, and then finally, the last axiom here of fields that we need is this one: a times b plus c equals ab plus ac. Okay, so this is the distributive property. Multiplication is distributive across the addition. Okay. All right, and so these are the 8 properties of fields that we need to have in our toolkit as we go forward, because what we're going to be doing is we're going to be proving a lot of things that are going to be pretty subtle, and we're going to be falling back on some of these properties of fields in order to accomplish those proofs. Okay, so just a little bit more along this topic. Now in practice, I guess I should say, in practice, this A inverse, this multiplicative inverse, is usually denoted as 1 over A, right? And usually that's what we're thinking of, right? So as an example of the number 10 in the rational or real numbers, the multiplicative inverse would be, you wouldn't write 10 to the negative 1, though if you did, it wouldn't be wrong. It just would be more convenient to write 1/10, right? Certainly for the arithmetic. So we typically will just we'll denote the multiplicative inverse as the reciprocal. And I guess I should say we'll just write A minus B instead of A plus negative B in the case of the additive inverse. So this is where division and subtraction come from. They're really addition and multiplication, but just with inverses, right? So you can really, you probably, if you're at this point in your career, you kind of recognize that, oh, indeed, there really are just two operations. It really is just multiplication and addition. Subtraction is just addition with negative numbers, or in this case, addition with the additive inverses. And division is really just multiplication with a fraction or something. Right? It really is just a different kind of multiplication. Now, in addition to these 8 properties, there are a few others that we need to look at, and those others are going to be certainly new, I think, to everybody. They're kind of things that don't really come up too much in abstract algebra if you've been there, and if you haven't been there, you certainly wouldn't have seen it elsewhere. And these are going to be the order properties of the real numbers. The order properties of the real numbers. Now, there's going to be 2 order properties, and they all have to do with this set, which we will denote as P, which basically stands for the positive real numbers. Okay, so the set R contains a subset P, and you can think of this subset as just being the positive real numbers. Okay, so the set R contains a subset P, the positive real numbers, which satisfy the following 2 properties. Okay, satisfy the following 2 properties. The first one is that if A and B are in P, so if A and B are positive real numbers, then if A and B are positive real numbers, then the sum of A and B and the product of A and B are also positive real numbers. So A plus B is in P, and AB is in P. So when I add them together, I'm in P still, and if I multiply them together, I'm in P as well. Right? So basically what we're saying here is that the positive real numbers are closed under these 2 operations. Okay. And the second property is that if A is a real number, then one and only one of the following is true. Then one and only one of the following is true, right? So what are those? So first of all, if A is a real number, A could be a positive real number, meaning A is in P. It's also possible that negative A could be a positive real number, right? Meaning that, of course, A is not in P. If A is not in P, then negative A may be in P. The third option is that A equals 0. Okay. All right, so if A is a real number, then it's either positive, or its additive inverse is positive, or it's 0. Okay. Now, any field which contains a non-empty subset satisfying these two is referred to as an ordered field. So any field with a non-empty subset satisfying these two conditions is called an ordered field. Okay, it's called an ordered field. Now, for the real numbers, we assume the existence of P. Okay, so for R, we assume the existence of P. For the rational numbers, if you think about that, that would be P intersect Q. So it's going to be basically all of the positive real numbers that are also rational numbers. So for Q, P intersect Q is such a set. So it's such a set, and it can be shown. It can be shown that P intersect Q is equal to P over Q, such that P and Q are integers, Q is non-zero, of course, and P times Q is a natural number. Okay, so that's something that could be shown, and I think you could imagine really that's not hard to believe, right? Obviously, we're just defining rational numbers here, and then this third condition just says, well, if we're talking about a positive rational number, then the numerator and the denominator have to either both be positive or both be negative, right? Which would satisfy this condition here. PQ is in N, right? N being the natural numbers. Okay, all right. So I know this is kind of a lot, and we're just kind of plowing through it. But in order to kind of set the stage for the least upper bound property, we really do have to go through some of this detail. Okay, now all of this ordered field idea, all of these ordered field ideas, is going to drive the following conventions. These are things we've been doing for a long time in math, but we maybe didn't know really where it came from or why we could do it. So this drives the following, right? So if A and B are real numbers, then if A minus B is positive, meaning it's in P, and so kind of the way to say that would be A minus B is greater than 0, then we can write things like A is greater than B, or B is less than A, right? So this concept of greater than less than all kind of comes from this idea, or it's based logically on this idea of the existence of the positive real numbers and the fact that real numbers are an ordered field. Now, when we write A is greater than 0, right, or 0 less than A, what we really mean is that A is in P. Right, that you should take those two things as being exactly one means the other. Right, when we say A is greater than 0, what we're saying is A is part of this subset of the real numbers that we call P, or the positive real numbers. Okay. Right, so all this ordering business comes from this idea of the real numbers being an ordered field. Okay. All right. Now, so all of that is kind of prerequisite for the following consequences of ordered fields. So the following are immediate consequences of R being an ordered field. They're immediate consequences of R being an ordered field. Let me put a little extra here. Okay, so first thing is if A is greater than B, then A plus C is greater than B plus C. Okay, that would be... Now, we could prove this, and we could prove it using just the axioms that we introduced at the beginning of the section and the ordered field properties. Okay, another one would be if A is greater than B and C is greater than 0, then AC is greater than BC, right? So when I multiply by a positive value, C, then the ordering remains the same. Okay, so these are things that we take for granted. I mean, we take all of these things for granted. If you were in calculus, you would take this stuff for granted. But in real analysis, these all have to be sort of established in a rigorous way. They all have to be based on something, right? Now, similar to 2 is if A is greater than B and C is less than 0, then what happens? Well, AC is actually less than BC then in those cases. And again, this could be proven based solely on the field assumptions, the field axioms from the beginning and from the order properties. Okay. Number 4, if A is not equal to 0, then when I square A, I get something positive, right? You could say, i.e., A squared is in P. Right, it's not wrong to say that, but I don't really, what we're trying to do is kind of get back to what we're used to thinking about, right? But in proving this, you would invariably use this fact that A squared is in P. That would be equivalent to identifying that A squared is greater than 0. Okay, and then finally number 5, if A is greater than 0, then 1 over A is greater than 0. And if A is less than 0, then 1 over A is less than 0. Okay, so if you have an element in P, then its multiplicative inverse is also in P. And if you have an element that's not in P, then its multiplicative inverse is not in P. Right, so you could contrast that with your intuition about the additive inverses. If A is in P, then negative A must not be in P, right? We saw that as one of the order properties, in fact. Right, but when it comes to the multiplicative inverses, they're either all in P or all out of P. Okay, now we're not going to prove all of these, but we will prove one of them. We'll prove number 2. Right, and the goal here is really just kind of to help illustrate the method of proof, right? And the fact that we can derive all of this based on the simple assumptions of an ordered field. Okay, so let's prove this. So we're trying to show that if A is greater than B and C is greater than 0, then AC is greater than BC. How can we prove that? Well, let's take a look here. So let's let A be greater than B. And so what does that mean? That implies that A minus B is in P. Now, if C is positive, so if C is greater than 0, then C is in P as well. Okay. Now, by the order property number 1, now what was that one? That said if A comma B are in P, then A plus B is in P, and A times B is in P. All right, so by that property, we know that A minus B is in P, and C is also in P, so A minus B times C must be in P. Right, so here's an element in P, here's another element in P. When I multiply them together, they must be in P as well, that product. Okay, and so then by the distributive law, A minus B times C is equal to AC minus BC. That must be in P. And what does that mean? Well, remember what we said. We said that if something minus something is in P, then that implies the inequality, right? So that's going to imply that AC is greater than BC, right? Which is exactly what we were trying to prove. Okay, so that's the method of proof that you would want to rely on. Right, so notice there's nothing in this proof. It relies 100% on the order properties and the field properties given at the start of the section. And that's really what we would like to have most of the proofs in this class kind of fall back on. Most of the stuff that we're going to prove, we would like it to be ultimately derivable from that set of assumptions or axioms. Okay, all right, and I would encourage you to, similarly try to prove the rest of these. So we did 2. One's going to be similar, but of course there, well, give it a try, right? So if A is greater than B, then A minus B would be in P, and so you could use that as a starting point, right? And you might have to check a couple cases, right? But all of these are going to be really kind of similar. Well, they may have different moves for sure, but they're all relatively easy to derive from the assumptions, the axioms given at the start of the section. Okay, so now what we want to do is we want to move on to the least upper bound property. So next we'll start breaking down the least upper bound property. Okay, so we want to start kind of breaking this down. Now, what we'll see is that while both R and Q are ordered fields, right? So this is going to be kind of one of the big results. While R and Q are both ordered fields, only R, the least upper bound property, holds for R alone. So it does not hold for Q. So Q is an ordered field, but R is very special. There's something going on with R that isn't there for Q, right? And that something kind of boils down to this least upper bound property. Okay, so let's go ahead and start by defining what does it mean for something to be bounded, for a set to be bounded. We'll start with that. So, definition. A subset E of R is bounded above. So it's bounded above if there exists a beta in R such that X is less than or equal to beta for every X in E. So for every X in E. Okay. So a subset E of R is bounded above if there exists some number, some real number beta, such that for every x in B, x is less than this beta, right? And then we would say such a beta is called an upper bound of E. Okay. Pardon my bad handwriting. So a subset E of R is bounded above if there exists a number, a real number beta, such that x is less than or equal to this real number beta for every x in E. Right? Such a beta is called an upper bound of E. Right? Simple concept. This is a pretty simple concept. Right? So example would be, this will be a silly example, but just to make sure that you can recognize that this is a relatively simple concept, let's let A equal the set of x such that 0 is less than or equal to x, which is less than or equal to 100. Okay. Then 99 is not an upper bound on A. Right? Obviously, because there's something in A that's greater than 99, namely 100. Right? But 100 is an upper bound on A. Right? So everything in A is less than or equal to 100, and so 100 is an upper bound on A. And if there's an upper bound for a set, then that set's bounded. All right, so A is bounded. Okay, so that's all we mean. That's all we mean. We have to start with that. Now, we could similarly define bounded below and lower bound. We could say a subset E of R is bounded below if there exists a beta in R such that x is greater than or equal to beta for every x in E. Right? Such a beta would be called a lower bound of E. Right? So you can take the time to write that out if you like. Okay. Let's see another example. Let's let A equal this set: 0, 1/2, 2/3, 3/4, and so on. Right? Infinite set. And so another way to write this is to write 1 minus 1 over n such that n is a natural number. Right? N is equal to 1, 2, 3, and so on. Right, so you see that the first one is 1 minus 1 over 1, which is 0. And then you get 1/2 when you go 1 minus 1 over 2, and then 2/3 is 1 minus 1 over 3, etc. And so what does this set kind of look like? Let's just think about it on the number line. Sometimes it's helpful to kind of write these out. So on the one end, you've got 0, which is the first element of the set. And then it looks like, we'll say that this is 1 here. Okay. So then you've got 1/2 is the next element in the set. Okay, and then 2/3 is the next, which would be roughly, I don't know, right about here, let's say. And then 3/4, right, and then 4/5, and then 5/6, right? And you can see what's happening. These numbers are going to get extremely densely packed up here towards 1. Are they ever going to exceed 1? No. Are they ever going to be equal to 1? No. Right, so 1 minus 1 over 10 million is very close to 1, but not 1. Right, so technically on this end of this set, we would have something like this. We would have an open bracket, an open parenthesis, meaning that 1 is not included. Right, but you can see we start at 0, and then we go to 1/2, and then 2/3, 3/4, 4/5, 5/6, and it just gets closer and closer and closer until eventually the points are virtually on top of each other as we get closer and closer to 1. This would be an example of a set that's bounded. Right? So a is bounded below by basically any real number less than or equal to 0. A is bounded below by anything less than or equal to 0. Is it bounded above? Yeah, it's bounded above by any number greater than or equal to 1. A is bounded above by anything greater than or equal to 1. Okay, and so you can see that from the picture. And obviously, whatever number's here, this is 1.1, then it's an upper bound on A. Okay. Let's see another example. So not all sets are bounded, as you can probably imagine. Let's consider n, the natural numbers, right? 1, 2, 3, and so on. Now the natural numbers are bounded below by 1. It's bounded below by 1, but n is not bounded above, right? There's no beta in the real numbers, right? There does not exist a beta in R, right? There does not exist a beta in R such that n is less than or equal to beta for all n in the natural numbers. Right? There's no large, and this all kind of comes from that. There's no largest natural number, right? It just keeps going and going. So as soon as I pick a beta, I'll have to pick another beta because there'll be a natural number larger than my beta. Right? And so on the surface, I know that it can seem like this is all very obvious and maybe painfully obvious, but it's very important to start thinking about these things and to not always assume that what seems obvious is true, right? In this case, it is true that the natural numbers are not bounded above, but there'll be a lot of examples where you'll say, oh, such and such is an upper bound on such and such a set, and it'll be like, oh, that may seem obviously to be true, but it's not true, right? So you have to be very careful in real analysis to look at something, give something a second look, really be willing to fall back on the definitions, right? So in this case, we can say that n is not bounded above because there does not exist this beta in R such that n is less than or equal to beta for all natural numbers. Okay. One more example. And this one will be a little more complicated, a little less obvious. Let's let B equal the set of rational numbers, so R in the rational numbers, where R is greater than 0 and R squared is less than 2. Okay. And so intuitively, when we kind of think of what this set is, we can imagine that this set B is really all of the rational numbers between 0 and the square root of 2. So intuitively, this is just all of the rational numbers between 0 and the square root of 2. Okay, so you can kind of think of it as this. This is all of the, so B is basically all of the R and Q such that R is in the set 0, or in the interval 0 to the square root of 2. You can kind of think of it like that. It's another way to think about it. Right, so on a number line, you've got 0, and then somewhere out here to the right, you've got the square root of 2. And we're really talking about all of the rational numbers in that interval. Okay. Now, we can clearly see that 0 is a lower bound, right? So 0 is a lower bound. And it's pretty obvious, right, that square root of 2 is an upper bound. Okay. But what's really kind of interesting about this example, where I want to kind of take this, is I want to go towards this idea that while B is bounded, and so this is one of those kind of fascinating opening ideas here from real analysis. So while a set may be bounded, that doesn't necessarily imply that the set has a largest element. Okay, and that's the case here. Now B is bounded above, but B, the set B, does not have a largest element. So it's bounded below, square root of 2 is an upper bound, but B does not have a largest element. Okay, now the key thing here is B does not have a largest element. Now, square root of 2 is an upper bound, but notice square root of 2 is not in B. Okay, so that's kind of an important piece of it there. Okay, so B does not have a largest element. Now, what do we mean by largest? By largest, what do we mean? Right? We mean an element alpha. We mean an element alpha in B, not beta, such that P is less than or equal to alpha for all P in B. Okay, that's what we would mean. If there was a largest element in B, it would fit this definition, wouldn't it? You know, if alpha was the largest element in B, then everything in B would be smaller than alpha, right? And alpha would be a member of B as well. But notice in this case, we can't find such an element. Okay. So such an element, such an alpha does not exist for B, right? The set that we've defined here. Sometimes it does, right? I could give you an infinite variety of examples where such an alpha does exist, where there is a largest element. Obviously, you've seen those. But here's a set that is bounded above but doesn't have a largest element. Now, how can we show that there's no largest element? What could we do to show that there's no largest element? Well, there's a couple ways to do this. The way that I'm going to do it is what I'm going to do is I'm going to select an arbitrary element from B. And then I'm going to show that I can always construct another element that's larger than it and is also in B. Okay? I'll show it by selecting an arbitrary P from B, right? And then showing that I can always, no matter what the P happens to be, I can always construct another element Q from P where Q is larger than P, it's greater than P, and Q is an element of B, right? So you give me your candidate for the largest element of B, and I immediately give you something else in B that's bigger. That's the nature of this argument. Right? So whatever P you say, hey, this is the largest element in B, I'm going to say, no, it's not. This is bigger. And then you say, okay, well, that's the largest element in P. And I say, no, okay, actually, this one's bigger than that one. And we go on like this forever. Right? So this argument is going to be of that nature. Right? No matter, it's going to be, say, whatever you give me, I'm going to find something bigger in B. Okay, so let's do this. And a lot of analysis proofs are going to, well, I mean, they're not all going to look like this, but this is the kind of thinking that you'll have to be able to do in this class, because it's just this is a tricky subject. Showing that a bounded set has no largest element is a tricky ordeal, and so this would be an example of how we might want to think about it. So first, let's let P be in B. This is just given, and let's define our Q. We'll say, that looks like more like a G. Q is equal to whatever you give me for P, I'm going to add to it, and I'm going to say P plus 2 minus P squared over P plus 2. Okay. So this is going to be my candidate for Q. You give me a P, I just calculate Q based on P. You can see that this Q is just P plus, it's a function of P, right? So whatever P happens to be, I can calculate a Q. Okay, let's do a little bit of algebra on this. All right, and so just let's get a common denominator of P plus 2 and kind of simplify this. So this would be like P times P plus 2 plus 2 minus P squared all over P plus 2. Right, and you could simplify this a bit more, and what you would find is that Q is equal to 2P plus 2 over P plus 2. Okay, so all I've done is just some algebra. Okay, now how do I know that Q is greater than P? Let's start with that. Okay, so first, we know that Q is greater than P, because why? Well, because 2 minus P squared over P plus 2, that's in P. Right, so specifically, right, 2 minus P squared is greater than 0. Right, and right, so since P is obviously from B, given the nature of B, right, so 2 minus P squared must be greater than 0 and in P. Okay. Okay, and then we would say since P is in B and P squared is less than 2, also P plus 2 is in P. Right, so basically the top is in P and the bottom's in P. So the whole thing's in P. Right, and so what are we doing here with this piece? We're saying Q is equal to P, a positive number, plus a positive amount. Right, and that's going to mean that, you know, Q, whatever it happens to be, is equal to P plus some more. Right, so that implies that Q is greater than P. All right, so that part's relatively easy to see. That part's straightforward, not a problem. What about, how do I know that Q is in B? How do I know that Q is a member of this set B of rational numbers between 0 and square root of 2? How do I know that? Well, for that we have to do a little bit of work, but it's nothing we can't handle, right? For that we could say, well, here's what we'll do. So to see that, so what we're going to basically do is we're going to, here's what we're going to do, right? So to see that 2 minus q squared is in P, that's what we're going to show, right? If I take the top of the bound and I subtract off whatever q squared happens to be, I need to have a positive, it needs to still be a positive number, right? Remember how we defined B, right? Remember B was equal to the set of all rational numbers such that r is greater than 0 and r squared is less than 2. Right, so what we're going to do is we're going to say, okay, 2 minus this number needs to be a positive number in order for r squared to be less than 2, in order for it to satisfy this upper piece. Right, it's certainly greater than 0. That's not a problem. That we've got that piece. But how do we need to establish this upper piece. So this is the part that we have questions about. Right, so what is 2 minus q squared? Well, I know what q is up above here, right? I've got q written out. And we're going to specifically use this version, right? So this is just an algebraic derivation, right? So this is what we use really for part 1. Part 2 is going to be better served with this piece. So 2 minus q squared is equal to 2 minus 2p plus 2 over p plus 2 squared. This is just q. All right, so 2 minus q squared is equal to 2 times this thing. And we can, oh, sorry, this should be 2 minus there, sorry. And we can do some algebra on this, all right? So we can say 2 times, we're going to get a common denominator here, 2 times p plus 2 quantity squared minus, and then instead of 2p plus 2 squared, I'm going to write minus 4 times p plus 1 squared all over p plus 2 quantity squared. Right, and I can expand all of this. And so I would get 2 times p squared plus 4p plus 4 minus 4 times p squared plus 2p plus 2 all over p plus 2 squared. Okay, now when I combine this numerator, a lot of things simplify. So I'll just write this out, and you can take a second and break it and make sure you see how this happens. But basically, you've got 2p squared minus 4p squared. So you've got minus 2p squared on top. A lot of the other stuff cancels away, and what you're left with is minus 2p squared plus 4. Everything else kind of disappears. Okay. And so then, let's do one more thing just to make the reasoning about this really clear. We can factor out a negative 2 here. So negative 2, and then it would be p squared minus 2 all over p plus 2 quantity squared. Now, what is going on up here? So what is this? Is this in P? This needs to be in P. And in this form, we can easily check whether it's in P or not. So this is obviously a negative. What about this thing here? Is this positive or is this negative? This is negative. Okay. So the top is a positive value. So the top is in P. What about the bottom? The bottom is obviously in P, right? So this is positive, right? So I've got a positive over a positive, right? And so that implies then that Q is in P, right? So what do we have here? So 2 minus Q squared is in P. That implies that 2 is greater than Q squared. 2 is greater than Q squared. And we already checked that Q is greater than 0, and now we can see that 2 is greater than Q squared, so Q squared is less than 2. And so that implies that Q is in B. Right? So Q is in B. Right? So remember, up here, we showed that Q is less than P. You give me a P, I can find a Q that's bigger. And what we've shown now is that not only is Q bigger than P, but Q is also an element of B. Okay, so that's exactly what we needed to show, right? So then, what we could say is that since 2 minus q squared is in P. Oop, P, not R. Sorry about that. P. Since 2 minus q squared is in P, and q squared is less than 2, we know that q is in B. Okay. So for any P you produce, I can create a Q based on your P. So for any P you produce, I can create a Q based on your P that is 1, Q greater than P, and 2, Q in B. Okay, and this shows that B has no maximum value. This shows that B equal to, remember the R and Q, such that R is greater than 0 and R squared is less than 2, has no maximum value. Okay. Right, so here we have a set. Right, here we have a set B, so B is bounded above, but B has no maximum value. I can always find something in B that's bigger than whatever you think is the biggest value in B. This is an interesting concept, right? So this is an interesting concept. Seemingly simple set, but now we have shown that while it's bounded above, it has no maximum value. There's no element in B that is the largest. Okay, very good. Very good. I think this will definitely have to be a two-parter. So I think I'll end part A with that, and we'll pick up with the rest of the least upper bound property, which we haven't even gotten to that yet, but we'll pick up in part B with a definition of the least upper bound of a set. Okay, so we'll be right back with part B.